Hi everyone, in this video we are going to cover section 4.2 titled Linear Approximations and Differentials. And we begin the section with a hopefully fairly familiar formula, the point slope formula that we've been using all along in chapter 3 to write the equation of tangent lines. Okay, so if I have a function y equals f of x and I want the equation of a tangent line at some point x equals a, what I want to do first is write this general formula a little bit differently using the notation that we're going to use in this section. So first off, I want to rewrite my m, the slope in my point slope formula. Where does that come from? Well, that's the derivative evaluated at the point A. Okay, inside of the parentheses, x minus the x coordinate is the one that we're given, A. And then the y coordinate, that's what I get when I substitute a into the function. So we can rewrite this as y minus f of a equals f prime of a times x minus a. And then if I get y by itself, then it looks like this. Add the f of a to both sides. Y equals f of a plus f prime of a times the quantity x minus a. All that is the point slope formula that you've used throughout chapter 3, but written in a specific notation that we're going to use in section 4.2 for linear approximations. And what we'll do essentially is we're going to travel a little bit away from the point A and use this tangent line to approximate the y coordinate at points close to A. All right, so what the heck do I mean by that? Well, let me scroll down to this graph here. All right, and we have the graph of f of x equals 1 over x, and this equation, here at the bottom is the equation of the tangent line at x equals 2. Okay, so that work has been done for us. Here's 1 over x. This is the equation of my tangent line. If I zoom in on that graph, and that's what this arrow is doing, we're zooming in a little bit to the right of 2. So the equation of the tangent line is at x equals 2. But if we zoom in a little bit to the right of 2, say at 2.1, what we see is that the blue tangent line and the orange curve, 1 over x, are like super duper close together. The y coordinate on the tangent line is 0.475, and the y coordinate on the curve, the actual y coordinate, is 0.47619. So the argument there is that my tangent line is a pretty good approximation to the curve f of x equals 1 over x for points close to 2. All right, and that's why it's a linear approximation. We're approximating a function value with a line. All right, that's what's going on in this section. The general formula that we're going to use is the one that I have written on the last slide, except instead of y equals, it's L of x. That's our linear approximation function, f of a plus f prime of a times x minus a. Ingrain it into your soul. Remember it. You're going to use it often, in this section at least. So let's try out an example where we find a linear approximation for root x, and we're using x equals 9, and we're going to approximate the square root of 9.1. Now, I know that I could just punch the square root of 9.1 in my calculator, but then I'm not doing calculus. All right, so here are the steps. Okay, here's what we're going to do first. I have my f of x is equal to the square root of x. I can find f of 9, which is going to be 3. F of 9, the square root of 9, is 3. That's my f of a in the formula. Let me scroll up a little bit so I have more space. I also need f prime of x. The derivative of x to the 1/2 power is 1/2 x to the negative 1/2, but I'm going to write it as 1 over 2 radical x. Okay, if you can go right from radical x to 1 over 2 radical x as the derivative, you're going to save yourself like some brain power as we go through this. So that's my derivative. Now I'm going to take the derivative and evaluate it at 9, because I know I need that in my formula also. So this is 1 over 2 times the square root of 9. Square root of 9 is 3, so I end up with 1/6 there. All right, that's my preliminary work. Now I can set up my linear approximation function. L of x is equal to f of a. Well, let me rewrite it first. F of a plus f prime of a times x minus a. So let's substitute in what we know. F of a, that's 3. That was the first thing we plugged in. F prime of a is 1/6. That was after we got the derivative. And x minus a is the 9 that we started out with. That's a 9 there. So what this function represents, or what it does, is it gives us good approximations for square roots of numbers close to 9. This would give a bad approximation for the square root of 15. It would give a good approximation for the square root of 9.1 or 9.2 or 8.73. Okay? The further away you get from 9, the less accurate the approximation is. But close to 9, it's pretty darn good. All right, so let's find 9.1. So my linear approximation, L of 9.1. Notice I'm not putting the square root there. We're not doing any square roots in this approximation function. We're only taking the square root of the quote-unquote easy number that we know the square root of. So L of 9.1 is equal to 3 plus 1/6 times 9.1 minus 9. That subtraction inside of the parentheses, it gives me 0.1, and so let's simplify. This is 3 plus 1/6 times 0.1 or 1/10. And so if I type this into my calculator, I get 3.0167. So that is my my approximation for the square root of 9.1. So then the question is, how good of an approximation is it, right? And that's an important question if we're using this. How good is it? So if I take the actual square root of 9.1 in my calculator, 3.0166200625, etc. So we are accurate to nearly 4 decimal places. We're off by 1/10,000th, right? This is a 6 there, that's a 7 there. That's pretty darn accurate without actually taking the square root of 9.1. Now, if I wanted to use this to approximate, a different square root, I would need to go back to the beginning. Like, let's say, I'm not going to do a whole other example here, but let's say I wanted to approximate the square root of 15.9. Right? If I want to get the approximation for that, I would need to go back through. My function and the derivative are still the same, but the f of a, right, that would be the square root of 16, I know. My a would be 16 because that's really close to 15.9, and I know its square root. And then f prime of 16. And so we would just get a different linear approximation function for the square root of 16, or for numbers close to the square root of 16. And that's how we can extend this further to approximate other square roots. Next example that we're going to do involves a trig function, my favorite. I love trig. So my function is the sine of x. The point that we're using, that we're close to, is pi/3, also known as 60 degrees. And we want to approximate the sine of 62 degrees. All right. So here's how this one works. F of x equals the sine of x. Well, let's get f of a, f of pi/3, pi/3. That would be the sine of pi/3. The sine of pi/3 is the square root of 3/2. All right, that's the exact value of the sine of pi/3. Now I need the derivative. F prime of x, derivative of sine is cosine x. Then we evaluate it at the given point. F prime of pi/3 is the cosine of pi/3, and since I already have the sine of pi/3, hopefully you know the cosine of pi/3, that would be a half. All right, there's our setup, or our preliminary work. Now we can write our linear approximation function. L of x is f of a, square root of 3/2, plus f prime of a times x minus a. And every time the a, that's the pi/3, whether it's the pi/3 itself, evaluated in the original function, or evaluated in the derivative. Okay, so that's our linear approximation function. It will give me the sine of an angle close to 60 degrees. But here's the thing. In order for this to work, I need to be in radians. If you stay in degrees, this all falls apart. All right, so pi over 3 was given in radians, and weird of the problem to give me the other angle in degrees, but it's because 62 doesn't look nice in radians. So we do need to do that conversion, though. So if I have 62 degrees and we're converting that to radians, we're going to multiply by pi over 180, and I'm just going to write it as 62 pi over 180. And like, I could simplify that fraction a little bit. I could write it in decimal form. I'm just going to leave it like that. I'll simplify and get a decimal value at the end of the problem. Okay, so if we bring that down and plug it into our formula, into our linear approximation formula, L of 62 pi over 180, like that, square root of 3 over 2 plus a half, like this, 62 pi over 180. Ooh, this is something kind of cool. Actually, since I left that as the 62 pi over 180, we could get a common denominator here. My pi over 3 is technically 60 pi. Oh, this is going to work out nice. Over 180. And now I can do that subtraction. And if you got this as a decimal, that would be perfectly okay. I will eventually in my calculator, but I just want to see how this simplifies because I like stuff like that. And that's okay, I think. So we get the square root of 3 over 2 plus a half. Inside of my parentheses, 62 pi minus 60 pi is 2 pi over 180. Let's keep simplifying here. If I do this times 2, those cancel out. All right. And let's see. So we have the square root of 3 is over 2. Let's leave that over 2. I don't want to get another common denominator. Plus pi over 180. That's about as simplified as we're going to get. So let's approximate this in decimal form. 0.88, what is it? 88348 in my calculator. 0.88348 is the sine of 62 degrees. Go ahead and type the sine of 62 degrees in your calculator. See how close it is. It's super close. And make sure you're in degree mode in your calculator when you type that in. But the result should be very close to 0.88348. And we close out this section kind of on a related topic called differentials. And to start talking about differentials, the text goes into a lot of depth and detail. And if you find this interesting, then you should go and read through it and strive to understand it. I'm going to give a more surface level explanation of differentials, and that's okay, right? Linear approximations was the main topic of the section. This is kind of a closing subtopic, if you will. So we've used the dy over dx notation just to represent the derivative of a function, right? That is the derivative of y with respect to x. But remember, this comes from slope, right? This dy over dx, those kind of have separate meanings, almost separate from each other. Dy and dx, this is a small change in y given a small change in x. It's the slope at a point, right? That's how we've been using the derivative, right? It's the slope. The slope is a change in y over a change in x, a rise over a run, right? It's just, for derivatives, it's a really, really small rise and a really, really small run, because we started introducing this topic using like the limit as h approaches 0. Okay, so what I'm going to write now for differentials is, well, we know that f prime of x is the derivative of a function, right? And if I set that equal to dy over dx, our other notation for a derivative of a function, and what I'm going to do is I'm going to change this equation slightly by multiplying both sides by dx and multiply by dx over there. And so I'm going to write this as dy is equal to f prime of x times dx. And this right here is the key, that's supposed to be a star, there we go, the key formula for differentials, okay? And so what it represents is, and how it's used, is that a small change in x, this differential dx, a small change in x times the derivative at some point produces some small change in y. And it makes more sense in some application problems. Like if I'm blowing up this balloon, how much does changing the radius by this small amount affect the volume of the balloon? Okay, if I change the x by some small amount, how much does that change the y amount by? Okay, and so the way that we find that is by multiplying the derivative at that point times that small change in x. So now let's scroll down to an example or two. Okay, so this is for each of the following functions. We want the differential dy, when x equals 3 and dx equals 0.1. So if our x coordinate is 3 and we increase the x, change the x by a tiny amount, how much does that change the y by? All right, so A. Now the problem is given as y equals x squared plus 2x. I would prefer to go with f of x equals x squared plus 2x, and then my derivative f prime is equal to 2x plus 2. All right, so in order to write the differential here, so the differential equation looks like this: dy equals, and I'm going to put the f prime of x, 2x plus 2 in parentheses, times dx. So if I plug in my point and my small change in x, I will produce the small change in y. dy equals 2 times 3 plus 2 times 0.1. 2 times 3 plus 2 is 8. So this is 8 times 0.1, or 0.8. Okay, so again, what that means is that if I if I change the x by that's 1/10, I'm changing the y coordinate by about 0.8. Okay, that's A. Part B, y equals cosine x. I'm going to write it as f of x again, just so I don't get all confused with the dy's and the dx's. So we have the cosine of x, and then my derivative, f prime of x. Derivative of cosine is negative sine x. Now I can write my differential equation, dy equals negative sine x times dx. Oops, I lost my x there. There, I'm squeezing it in. All right, and then we can substitute the given values. dy is equal to negative sine of 3 times 0.1. And I could clean that up and write, maybe I'll put the negative 0.1 first. Negative 0.1 sine 3. This one, if I get it in decimal form, it'll just look real ugly. But that's as much as I want to write with this one. You could type it into your calculator if you want to. The change in y is 0.1 times the sine of 3, when the change in x is that 0.1. That's how much the y increases or decreases by. Okay, so that is the end of the section. The most important part is understanding how to find a linear approximation. Okay, and then this differential topic is very much related. But if it is a little bit more abstract, it is a little bit more confusing, especially if you look at all the detail that is available in OpenStax. And I encourage you to do it. It's super interesting. But for the purposes of this video, I don't want to go into any greater depth. Try the homework. Let me know if you run into problems that you can't figure out. Thank you for listening. Have a wonderful day.